know some of you got through problem number 1 in class, but not all of my classes did. So I just want to kind of discuss this one. Remember that GAW stands for given answer work. And if I read through this problem, it says a 600 gram block of aluminum. So I'm going to draw a block that is 600 grams. That kind of is part of the givens. And it has a CP of 0.9 joules per gram degree Celsius. This little guy over here is what we call specific heat. Now, is that important? Absolutely not. What is important is that this tells me a for every statement. So it tells me that for every 1 gram of aluminum to change 1 degree Celsius, we need 0.9 joules. Okay, that's what that tells me. And it also tells me that it's heated from 50 to 80 degrees Celsius, which means my delta T, or my change in temperature, is 30 degrees Celsius. Okay, and that's important to that whole change, right? And how much energy did this take? So my answer is question mark joules. So now I do my work. Okay, well, I've got a for every statement down there, and I should be in good shape. For every 1 gram of aluminum to change, sorry about the comma there, 1 degree Celsius, we need 0.9 joules. Okay, and then down here I've got my other for every statement. For every, well, I'm not changing at 1 gram, I'm changing 600 grams of aluminum to change 30 degrees Celsius, we need some amount of joules. All right, so I'm going from 1 to 60, and then I'm going from 1 to 30. And these are directly related, and we'll get back to this in just a second, but these are directly related. So I've got 60 and 30, so that means that that is times 1800. And you say, Mr. Swistak, 1800 times 0.9, that sounds kind of ridiculous. I got to do 9 times 18, blah, blah, blah. Here's the deal. You can think of 0.9 as being 1 minus 0.1, right? And 1 is just 1800. And 0.1 would just be 180. So if I subtract those two values, I get 0, 2, 6, 1620 joules. Easy stuff, right? All right, now let's take a look at what my LOL diagram should look like. LOL, LOL, oh, diagram should look like LOLO. Somebody might say YOLO, and you say, no, LOLO. All right, so I've got my LOLO, and remember that we're looking at phase energy and thermal energy. They both start with a little bit, and it's a solid object, so it's not a lot of energy that they start with. Solid object, so I'm going to show a solid object on the inside here. And I'm going to show that energy is being added because it said that it was heated. Okay, I'll just add a couple bricks of energy. Now, if this is a piece of aluminum and it went from 50 to 80 degrees Celsius, well, we already put a block of aluminum into boiling water, which is 100 degrees Celsius. So if I'm putting this in there, it's not changing phases. It is staying solid. So what is this energy being used for? Well, it's just being used to heat up those particles and make them move faster. So it's all going to the thermal or the moving energy, not the phase energy. Okay, and this brings me to another thing that I kind of wanted to talk about. Not related to number 1, but sort of related to number 1, and this is the idea of the 3 relationships. So when we're looking at energy, we're always looking at mass, change in temperature, and mass, change in temperature, and energy, right? So these 3 factors are the things that I'm looking at, okay? So if I look at the difference between mass and energy, if I want the same change in temperature, so again, if I have one mass that's small and one mass that's big, it takes more energy to heat the small thing or to heat the big thing and get the same change in temperature. So as my mass goes up, my energy goes up in order, and that's the important thing, is the constant. That change in temperature needs to be constant. So these two are directly related. Energy and change in temperature. Okay, if I have the same mass, so this time I have two pots that are exactly the same size. If I add more energy, little flame under this one, big flame, I don't know how to make it move, big flame under that one, then if I add more energy, I would expect more of a change of temperature only if the mass is constant. And those constants are what you have to think about. Okay, and then the last thing over here, if I look at mass versus change in temperature, okay, when energy is constant. So now I'm looking at, okay, now I've got a small pot and I've got a big pot. If I keep the energy constant under both of these, do they change temperature by the same amount? And your answer should be no. Look, this guy is going to heat up all these particles a lot faster because there are less of them than this guy does. It takes longer for this one to go. So by increasing the mass, I have made the change in temperature go down. Now this is going to approach zero but not reach zero, and thus the nonlinear trend, because if I add energy to anything, no matter how big, its temperature is going to change. Some of the particles will speed up, and that's an important distinction that you need to be aware of. Okay, now let's go over to numbers 5 and 6. So number 5 says an 800 gram metal block is heated from 10 degrees Celsius to 60 degrees Celsius using 8,000 joules of energy. What is the specific heat of the block? Okay, so this time again, I'm starting with my GAW. And so I've got an 800 gram block. And it's the change in temperature is going to be 50 degrees Celsius. And the energy is 8,000 joules. And they want to know what the specific heat of the block is. So now my answer, and this is my important part, is they want to know for how much joules does it take to change 1 gram of the metal 1 degree Celsius. Okay, so that's what I'm really looking for. So all I need is another for every statement, and I already have all the information necessary for that for every statement. So now I know that for every 8,000 joules, 800 grams of the metal changed 50 degrees Celsius. So I'm going to divide by 50, divide by 800, and we just talked about those relationships to energy. More mass means more energy. So less mass means less energy. So I'd divide by 800 and divide by 500. So I'd be dividing by 40,000. Okay? So I can immediately eliminate, basically I don't even need to put scientific notation. 3 zeros are gone. 8 divided by 40, well, 8 divided by 4 would be 2. So this would be 2 tenths. So it takes 2 tenths of a joule to change 1 gram of this metal 1 degree Celsius. My LOLOL would look exactly the same as the last one, because again, all I did was take a solid and heat it up. So you can figure out the middle part just by looking at that last problem that we did. Okay, number 6 says water is heated from 2 degrees Celsius to 22 degrees Celsius. What is the mass of that water? Okay, so let's take a look at this one. Now, this time, I would say that in my given, I've got a for every statement. For every 4 joules of energy, 1 gram of water changes 1 degree Celsius. And I know that I also have a change in temperature of 20 degrees Celsius. And my energy that I added this time is 1200 joules. And my answer I'm looking for is question mark grams, my mass. Okay, so let's talk about the work here. So I've already got a forever statement. And I'm going to just erase this real quick just so that I have it right here. I've got that forever statement already done. I'm just going to change the colors real quick. Well, in theory, real quick. Oh, for crying out loud. There we go. All right. So now I know, okay, for every 1200 joules, blank grams will change 20 degrees Celsius. Okay, so times 20 times 300, right? Okay, so now I need to think about my graphs. So now I'm comparing mass to change in temperature when energy is constant. And I'm comparing mass to energy when the delta T is constant. Well, if I change the mass and I want to keep the change in temperature constant, I need more energy. If the energy is the same and I increase the mass, remember we said little pot, big pot. Boom, inverse. Okay, so my delta T, I'm going to divide by 20 and I'm going to multiply by 300. Which means I'm really going to multiply by 15, I'm sorry. 15 grams. So 30 divided by 2 is 15. So I'm just multiplying by 15. Now, this time, my LOLOL looks almost exactly the same, except, or my LOLO, let's undo that. Make it big. All right, so this time I'm starting with a little bit more energy in the phase. And my thermal, let's start with a little bit more. Okay, and I'm heating it up, 20 to 22. So I'm not heating it a ridiculous amount. Let's put 2 bricks. It's a liquid, so let's draw our liquid. There's my liquid. And then I added 2 things of energy. Again, from 20 to 22, it's not going to change phases. So the phase energy remains the same, but the thermal energy goes up by 2. Oh, that's a terrible scale, but you get the idea. My phase energy is the same. My thermal energy is not the same, but my particles in the water then are moving a little bit faster. Okay, I hope that that helps you quite a bit. Make sure that you watch this video. If you're just copying this stuff down, it's not going to help you a lot. But if you're kind of going through and trying this on your own as we go, it's going to help you a ton. Okay, you feel free to watch it as many times as you need to. Come in for some extra help if you're still not getting it. I will see you tomorrow. Bye.